In Mod 8A, we are going to be talking about inverse functions. In order to talk about inverses, we need to do some definitions to begin with. Remember that a function is a relation, which is a set of ordered pairs, in which all the x values are different. A function is called one-to-one if all the y values are also different. To determine if a relation is a function, when we had the graph, remember that we used the vertical line test, which said that if you cross the graph one time for any possible vertical line, then that relation is a function. Now, if we know it's a function and we want to know if it's one-to-one, we use the horizontal line test, which works exactly the same way. If you draw any possible horizontal line through the function and you cross that function exactly one time, then that function is one-to-one. In our first example, we are being asked to determine whether or not the function is one-to-one. The graphs that we are given, we know are functions, so we know that they will pass the vertical line test. What we want to determine is whether they pass the horizontal line test. So on this first graph that is just a series of points, if we draw any possible horizontal line, do we cross that graph one time? Yes, we do. So is the function one-to-one? Yes. On our second graph, using the same idea, if we draw horizontal lines, will every horizontal line that we draw cross the graph exactly one time? Yes. So is it one-to-one? Yes. On our third graph, all I have to do is draw that horizontal line, and I see that I have crossed it twice. So is this function one-to-one? No. On this last graph, if I draw a horizontal line through that lowest point, I'm only crossing the graph one time, so that looks okay. If I move up just a little bit and I go through the open circle and the line segment, the open circle is not included in the graph. So the only place we are crossing is the line segment, and that still looks okay. But if we move up just a little bit, we are crossing that graph two places. So is this function one-to-one? No. The way that we determine algebraically if two functions are inverses is if both of the following statements are true. F composed with g of x equals x. You put the g function into the f function and it simplifies to equal x. And if you go the other way, if you put the f function into the g function or do g of f of x and you get the answer of x, then the functions are inverses. Both of them must be true. If only one of them is true, they are not inverses. We are being asked to determine if the two functions that we are given are inverses. The first example, we have a function f that is defined as x over 2, and our function g is defined as 2 times x. So first, we want to do f of g of x. That means put g into the f function for the variable. So we start our f function, and the very first thing is the variable. So we put the g function in where the variable was, and then finish writing the f function by putting over 2. Well, if you look, 2 over 2 equals 1. So what do we simplify to be? X. So far, it's looking good. Now let's do it the other way. Do g of f of x. So start the g function. It starts with a 2. And then it's times the variable. So where the variable is, we are going to put in the f function. Well, again, we have 2 over 2, which equals 1. So that simplifies to be just x. So are they inverses? Yes. For our next example, f is defined as negative x minus 2, and g is defined as x minus 2. Remember that we need to do f of g of x. We need to put g into f where the variable is. So we start our f function, which starts with a negative sign, and then it gives us our variable. So we replace the variable with both terms of g, and because it's 2 terms, I'm putting it in a set of parentheses. Then finish writing the f function minus 2. We need to distribute that negative sign. It will give us negative x plus 2 minus 2. Plus 2 minus 2 equals 0. So our simplified version is negative x. As soon as we see that we have negative x, not just plain positive x, we know that these two functions are not inverses. On this example, our function f is defined as x plus 4 divided by 3, and our function g is defined as 3x minus 4. Starting off by doing f composed with g of x. We start our f function, which immediately has the variable in it. So we're going to take out the variable and replace it with all of g, which is 3x minus 4. Then we're going to finish writing the f function. So the numerator still needs the plus 4, and then it all needs to be divided by 3. Well, plus 4 minus 4 gives us 0. So at this point, we have 3x over 3. But 3 over 3 equals 1, so our composition of f composed with g simplifies to equal x. It's looking good so far for these to be inverses. We still have to do the other version of g composed with f of x. So this time we start the g function, which starts with 3, and then we have our variable. So we are going to replace the variable with the entire f function, x plus 4 over 3, and then finish writing the g function minus 4. Well, when we have 3 times that fraction of x plus 4 over 3, we have a 3 over 3, which equals 1. So now we have x plus 4 minus 4. But plus 4 minus 4 equals 0. So this composition simplifies to be x also. So are these inverses? Yes. When the function you are given is a set of points, the inverse function is found by reversing the coordinates of the points. We're being asked to find the inverse function when our given function is the set of points 3, 5, 0, 2, negative 2, 3, 4, negative 7, negative 3, negative 5. First thing I want you to take note of is that when you are finding an inverse, you write that as f with a negative 1 exponent. That is our symbol that tells us that what's following is an inverse. Since this is a set of points, we just take those points and reverse their coordinates. So our first point becomes 5, 3. Our second point becomes 2, 0. Our third point becomes 3, negative 2. Fourth point is negative 7, 4. And the last point is negative 5, negative 3. And that is your inverse. To find the inverse of a function in equation form, there are several steps. First step, replace the f of x, g of x, or whatever the name of the function is with the letter y. Next, switch the y and the x. Now solve your new equation for y. Last, replace the y with the name of your function, f, g, whatever letter it was, with a negative 1 exponent on it to show that it's an inverse of x. So we are going to practice finding inverses of functions, and our first example is the function named h of x, and it is defined as 9x minus 3. Step 1 is to take out the name and replace it with y. So it becomes y equals 9x minus 3. Step 2, switch the positions of x and y. So it becomes x equals 9y minus 3. Step 3 is to solve that new equation for y. Well, the first thing that we want to do is add 3 on both sides. So I get an equation of x plus 3 equals 9y. Now, how do I get that y by itself? Divide both sides by 9. This gives me an equation of y equals x plus 3 divided by 9. Now that we have solved that equation for y, we go to step 4, take the letter y out, and replace it with the name, but have the negative 1 exponent on it. So it will become h of negative 1, the inverse function for h, equals x plus 3 divided by 9. One thing I want you to note, in the original function, we were multiplying by 9 and subtracting 3. In our inverse function, we have added 3 and divided by 9. Those things will always happen. The operations that you had in the original will be reversed in the inverse. For our second example, we have a function named g of x, and it is defined as x minus 9 divided by 11. Our first job is to take out the name and replace it with y. So it becomes y equals x minus 9 over 11. Step 2, switch the places of the x's and y's. So it becomes x equals y minus 9 over 11. Step 3, solve that new equation for y. Well, right now, the y is in a fraction that's being divided by 11. So the first thing I'm going to do is multiply both sides by an 11. This gives me 11x equals y minus 9. How do I get the y by itself? Add 9 on both sides. Our ending equation then is y equals 11x plus 9. Finish out. Step 4, take y out, put the name g back in, put the negative 1 exponent on it. So g inverse of x equals 11x plus 9. The last thing we're going to learn in this module is how to find the inverse function for a graph. To do this, we're going to use the idea that we talked about earlier of switching the coordinates for points on the graph. We're going to find points on our given graph and switch them to find the inverse graph. When you are finished, the results should be two graphs that are symmetric across the line y equals x. What this means is that if you fold the graph on the 45-degree line that runs through quadrants 1 and 3, they should match exactly. We are going to use the graph that we are given to find the graph of its inverse. So in order to do that, I'm going to find some point coordinates on this given graph. This endpoint has coordinates of x equals 6, y equals 7. This point where it bends a little has coordinates of x equals 5, y equals 0. And the other endpoint has coordinates of x equals 3, y equals -4. So our rules for finding inverses tell us to flip-flop the coordinates. So if we're going to flip-flop 6, 7, that means that x will be 7, y will be 6, is our first point on our inverse graph. We would have the point of x equals 0, y equals 5 for the second point on our inverse graph. And then we would have the point of x equals -4, y equals 3 as the other endpoint on our inverse graph. Now, by connecting those points, we get the graph of our inverse. To check ourselves, let's think about if we had the 45-degree line that ran through quadrants 1 and 3. If we folded along that line, would those two graphs line up on top of each other exactly? And they would. We are doing the same thing on this figure. So for the endpoint on the right, what are its coordinates? Its coordinates are x is 3, y is 6. The bend in this graph has coordinates of x is -2, y is 4. The other endpoint has coordinates of x is -4, y is -6. To graph our inverse, we're going to flip-flop our points. So for the right endpoint, our coordinates become x is 6, y is 3. Our bend coordinates become x is 4, y is -2. And the left-hand endpoint, the coordinates become x is -6, y is -4. If we connect those points, there's the graph of our inverse. To check ourselves, let's think about that y equals x 45-degree line that runs through quadrants 1 and 3. If we folded on that line, would those two graphs line up on top of each other exactly? That's what would happen, so we know that we have sketched our inverse correctly.